Alright, now we come to the second part of these principles of separations of CE. Remember that it is about high efficiency and the low consumption of reagents in capillary electrophoresis. And also, one of the highlights is its versatility. We can change different modes of the CE. And bear in mind that there are many approaches to optimize the separations. And keep in mind important factors to achieve the best peak shape and separation. Let's do a recap here. The various modes of CE separation operations. You've got the capillary zone electrophoresis, the MEKC, the gel electrophoresis, electrochromatography, CIEF, CITP, right? And the basis of separations are such, right? Know the differences because we will ask you to highlight them, maybe in your test. So there are additional separation mechanisms, right, such as ion exchange, complexing, because you want some of your substrate to interact with your capillary, right, particle interactions, and chiral separations. And you know that we're going to highlight the last part because it's so important in natural products. Most of these natural products and compounds are chiral in nature. So how are you going to separate the R and S isomer, or if you have a diastereomer, or you have enantiomer but with different chiral centers? This is going to be a problem, but luckily we have many forms of applications in CE for us. So one thing is, right, we do an inclusion of complexation using a chemical called CD. CD is short for cyclodextrin here, right? So it feels like a cone-shaped particle. It has a cavity, imagine like a pail, right? There's taper on the side, but it's hollow basically because it allows your substrate to go through, right? But using also the size exclusion principle, that you need to look at the size of the CD so that, right, your substrates can go through and not be stuck there. So what happens is, right, if your CD is large enough, right, you can allow these particles to go through. And the thing is, you will also want to make it charged or no charge, charge meaning a positive charge or negative charge, to have extra interactions with your substrate, so that you can separate the velocity of these particles up. Okay, so as per discussed just now, right, if your cyclodextrin are neutral in nature, then of course you'll follow the UF, uninfluenced and affected by the voltage, right? But if it's charged positive and negative, right, then you have either it will be the front or the back of the EOF. Now, what are some examples of the charged cyclodextrins? So for the positive charge, we use the amino group because your NH2 group can attain an NH3 plus charge, right, for the ammonium if you have a slightly acidic medium. And for the negative charge cyclodextrin, you have the sulfated part. Okay. So this is your cyclodextrin MEKC here, some of the little mechanism. So we notice that, right, both your CD and your micelles, right, are involved in this case. Here you form the micelles and you form a CD, and this is EOF moving from left to right. And you see that there are actually some competition between the micelles because the tail outside is hydrophobic in nature, and the CD itself, right, is it's like a cone shape, without the tip, and its charge also exhibit a lot of hydrophobicity. So these are some of the legends of the drawings there. Okay, so this example here will tell you about the selectivity of this reagent. Okay, so you can see that, right, if you combine the CD cyclodextrin with the micelles, it does provide additional selectivity because your E in this case, right, okay, your analyte can bind to these two particles, your CD, and informs micelle in different manner. So there's a bit of equilibrium exchange, right? So we can allow separation as well. Now, next part is the chiral separation by CE. Let me elaborate a bit further. So, of course, just like previous cases, you have the indirect separations and direct separation. Indirect means you your detector window here, right? Normally you have peak, but then if your substrate is there, then you see a drop. Direct means, right, there's normally no signal, but then when your substrate goes through, then you see a signal there. That's direct. Okay, so we're going to highlight a few of the direct separations here using, of course, we have covered CD, and then we'll go on to cover ionic liquids. Right, these are interesting compounds because they are liquid, but it's ionic. So how can something that's a strong electrostatic forces of attraction having a boiling point of lower than 100 degrees Celsius, right? Then we also talk about dual selector system, right, and some other parts of it. Really interesting there. And of course, we can highlight the monolithic phases, as you have a nano wall, a carbon tubing, okay? But here I'd like to really highlight the main difference in terms of the merits and the demerits between the capillary electrophoresis and HPLC, because you also know that you have done before in an experiment. Your HPLC also, you can change the column to have a current separation. Now, what are some of the advantages of CE versus HPLC in this area? Is about high resolution. Like I said, HPLC is high performance, but it's not the best in terms of resolution. Now, CE is low cost because one is you require a low sample, and also there's no need for Chiral column. Chiral column are extremely expensive because you just have to purchase the whole column that's made from a manufacturer. But the CE, the capillary, you can modify yourself internally. Also, it is simple and versatile, and you can change the coating within the capillary for Chiral selector. Now, the disadvantage of CE versus HPLC in this regard is that because it's so small, you use little amount of substrate, it's micro scale, so it's very difficult, for the collection in fractions, right? Which means that in a way, it's more of like a testing. Is you see what are the substance there and what are the migration time, but less of doing a real separation to collect what you wanted. You see a difference there, so it's more like detection analysis. Next thing is, right, because of the low UV sensitivity in the CE there, so we have a short path length, yeah, versus a column that much longer. And of course, we need to acquire new methods. You see that there's manufacturers from XYZ company, a few companies who make this column for HPLC. That's because it's a very stable and it's a business that they can sustain. Okay, so therefore there's still improvement for CE. Now this part here, I'd like to highlight why is it so important for chiral separation. But first of all, I'd like to introduce the term here is called the pharmacokinetics, right? It's a study of how the body affects drug, right? And how the drug affects the body. So the pharmacodynamics is the study of how a drug affects the body, okay? This part here. So it's, do not get confused about here. Now the pharmacokinetics, right? Sometimes it's described as what the body does to the drug, meaning that, right, the movement of a drug into, right, through the body and out of the body. Does it get absorbed? Does it get retained? Does it interact with some parts of your blood vessels or different organs? And the time taken for it to be absorbed, right? What's the bioavailability, right? And the distributions around the systems, the metabolism, excretion. For the PD, in this case, your pharmacodynamics, on the other hand, it's a study of the biochemicals and the physiological effects of drugs, right? When you take in, and then how does it affect the body in terms of the reaction? Okay. Now, as you might have known here, it is important to do the chiral separation because we have a very disastrous example some years ago, right, in Germany. There was the thalidomide incident here where, when the pharmaceutical company at the time didn't separate the enantiomers of a thalidomide, right? But little did they realize that one of the enantiomer could cause deformed babies, right? So when the babies were born here, is teratogenic, meaning that some of the limbs were gone. Here is so bad because it was used as a morning sickness drug for pregnant women, but it didn't know that one of it was so harmful. So we all learn from history, from accidents, right? And since then, the pharma companies has a huge responsibility to make sure in the testing, right, to make sure that they separate the enantiomers, right? Here we see what are the different chiral analysis to separate the techniques here. So you can see LC, liquid chromatography, one of the lowest cost, still has a high proportion, right? GC 12.7%, CE is a bit more, right? And of course you have your SFC, in this case supercritical fluid chromatography. So we can tell that it is also in a way conditioned by the cost involved. Okay, here a schematic diagram to show how capillary electrophoresis chiral separation mechanism. So you have this CD here. Remember this cone shape, right? And when you have your S and your R isomer, right? So there's a difference in affinity towards your cyclodextrin. And when you have a difference in affinity, there's also a difference in mobility as a whole here, because now you have a free isomer. This is tagged along with the chiral selector, right? So same goes for the R. So when you have this exchange, it's a different rate here. You also have a different proportion of this S and your R, okay? Depends on the equilibrium shift. So effectively, you are comparing the amount in the complex form and the free analyte of your R and S isomer. So therefore, there must be a difference between the affinity, right, of the S and R isomer, right, for it to be successful. In this case, we introduce to you the Rand mobility difference model here. You can see that it is more just an equation that you will do some substitution. We mentioned before that the mobility of the S and the R isomers are different because of the exchange in the complex form and the free form here. Okay. Here, how would you measure the mobility? Again, look at the unit here, right? This is the difference in your mobility, meter square per second per volt. Okay, it's caused by the potential difference across the two terminals, and of course it's by area because it's moving by bands, and also it's about the kind of velocity, so it's about the speed involved there. Here you see a very similar drug, and you can see a difference in the mobility under different chiral selector here. Okay. All right. So we do experiments in the lab to see what is the optimum concentration of the chiral selector depends on the Ks and Kr. And to do that, right now we still can't calculate, but we have to perform experiments and then perform and put the dot and see where's the turning point. And one may ask, how come we need to find the optimum concentration? Can't we just spam, right? But you don't want to waste chemicals, and if you remember the column, you don't want to saturate it with cyclodextrin too much because they become foreign particles. What you want is to separate the two enantiomers. So here are some of the sample picture of electrophoregram after you have separated them using CE. This is how it looks like. So before you have a chiral separation, you have just 1, 2, 3, or 5 different substrates here, right? Different R chain length, but if you have chiral, then each of these peaks separate into 2 because now you can see the chirality moving at different speed. Of course, 1, 1, then 2, 2, then of course R 3, 3, 4, 4. So here I just for example 3R, 3S. This one could be 1R, 1S, or the order. We haven't done this investigation, but I want to say that there will be a slight difference in their mobility, okay, for the enantiomers. Here you can see that there are also other chiral selectors for CE, for chiral separations, but the most frequent reported use in the journal articles is still a cyclodextrin, see, in terms of publications. And you might also see posit what is the reason for the high usage of CD here. Okay, cost is definitely one of them here, and of course it's about you're able to do some modification in terms of the structure. So you see here you have 8 different CD cyclodextrin derivative, right? It's more of organic chemistry, how you change this extra arm here, right, in terms of changing affinity, having a bit more polar groups in your two diimine group, or you have introductions of this aromatic ring that will affect the binding affinity, and that causes the shift in the complexations and the free form of your analyte. Okay, and there are times you see these three here I'm pointing to, 1, 2, and 3, right? You also might want to apply some of these chelating inorganic kind of mechanism, right, to clamp to your substrate so that it's unable to be discharged so readily here. So for more, you can read from Macaroni and Vecchio in electrophoresis. Now in this case, we give some more complex example, complex pun intended, but complex in the structure, because now you see 2 or 3 arms, right? And putting a copper center there. Don't have to know what are these, but I just want to say that this is you can modify your cyclodextrin in a complex manner or even a simple manner to exhibit the difference in the R and S binding. Okay, so in this case, you have a mixed complexes of the histamine substrate substituted your beta cyclodextrin with the tryptophan enantiomer. Okay, so this is just a no tryptophan. You have the L isomer, you have the D isomer, and mind you, as a reminder, the D and the L has no link with the R and S for the chiral center. Okay. So another snapshot of this electrophoregram here, because you know ibuprofen, phenylprofen, ketoprofen, all these are similar kind of NSAID drugs, right? And they also are chiral, so we can separate them. You see, like remember just now 1, 1, 2, 2, 3, 3, right? These are the profen drugs here. Okay, note that right in the condition, we always can spot to see whether it's chiral, but by looking at this compound added. So here we have a trimethyl beta cyclodextrin, TM beta CD. Okay, that's one clue. The other clue could be a paired kind of signals there. So here you see a cross, right? Without cyclodextrin, 1 signal. With the CD, you have 2 signals but very close. How can you separate and resolve the signals well here? So we can use another form of CD. You see HP beta CD, right? There's the RS is higher. Basically, you have more difference in the mobility. And another one, you have a DM beta CD. And these are all just slight differences in the structure modification, right? And then there are some it's lower, so the peaks are closer, right? Just to compare with a methylated derivative. Another part to see which is the best CD to use, right? If you want to separate to resolve, in this case, your fluoroxetine. Okay. So I think to summarize, you can always look carefully either at the signals to see, okay, do you think that this is for enantiomeric separations, right? Did they use CD? Then you need to look at the data and information. Oh, okay, this is 2% sulfated beta CD. So look out for this beta CD as a guide, right? To elucidate if these two are enantiomeric form or they're totally different substrate. Okay. Next part again similar. You see that right? There's the pattern of the signals are pretty similar. I would say similar to NMR. It's like in a way symmetry, because after all R and S differ only by the handiness, right? So it's not like one is extremely tall, one is extremely short, right? And the shape are pretty similar as well here. Okay. In this case, we highlight some positively charged cyclodextrin derivative here. Okay. Some structure, so you have your C-dan, your ethylene diamine derivative, right? Single arm, and the right side more complex. You have a bit of like sugar form, while your cysteamine bridged hemiferrodextrin. Okay, for more information, you can read more, but I just want you to look at the main idea. Why can it be positively charged? Because if you have your amine group that's easily protonated. Okay, so by the way, this THCMH, right? So how they got is a 6A, right? 6D dioxy 6A 6D 6 prime dioxy 6 cysteamine alpha prime trihalose beta cyclodextrin. So I just trying to articulate what is the chemical formula, right? But please don't memorize here. Okay. Of course, you might think, oh, now so powerful. We have got your CD. You can modify it in derivative, but there are actually limitations. Now, these are some of them. First, you want to buy something that's reproducible. you want your separation to be reproducible, so it must be commercially available. If it's not, then I would say we should want to minimize using it. And the thing is, because it's charged, right, your CD is charged, so they become part of the substrate. They get affected by the current after all, right? So this CD analyte also can migrate to the one of the electrodes, your cathode anode, and this entails performing your experiments under either the direct or inverse polarity conditions. And of course, because you have your inherent CD themselves, after all, they are also organic compounds that, put inside there, they need to be separated. So there's also some intrinsic mobility, right, that causes excessive electron dispersion and also maybe broad asymmetric signals. So the separation might be diminished. So therefore, if you recall a few slides just now, we need to look at what is the Cmax, what is the right amount of the CD, the chiral selector you want to put inside. Not too much, not too little, but just right. So another chiral selector you got to know is your crown eater. Crown eater after CD is the second most common chiral selector. So over here, this is really your host gas chemistry here, right? Bit of material organic science. Now, first thing to note is, right, how do you derive this 18C6H4 there, right? So we see 18C means, right, in your ring here, there are 18 atoms. So you have 2, 4, 6, right, 6 carbon, and then your 6 oxygen here. These 6 here represent your 6 oxygen that's able to act as a Lewis base to donate your lone pair of electrons to form dative bond with the center. In this case, hydrogen bond, right, with the center. Okay, so you see in this case, right, you separate your L dopa and D dopa using your crown eater.